is, what are discrete functions and continuous functions, and what is domain and range. So in general, we're going to be talking about functions, and these are simply sets. Sets are denoted as with these curly brackets, and they are a group of objects. Now this group of objects is also equal to this. Order does not matter with sets. And in fact, repetition doesn't matter. We could repeat the number 3 twice if we wanted to. So all of these sets are equal. To denote that there are certain elements in this set, we would refer to, for instance, that number 3. 3 is in that set. 3 is an object in the set 3, 4, 5. So that's one notation that you will see in your homework. Also, we know that the object 4 is in that set. 5 is in that set. And we can also denote this as 3, 4, and 5 are all values that are in that set. So those are some notational aspects of that. What's an object that is not in that set? Well, 6 is not in that set. So the symbol for not is you just put a slash through it. Think about not equals. Not equals just has a slash through it. So that's just to get started. Now, a function in general is a set of points where every input has exactly one output. So a set of points, well, that would look like a set with different points. Well, this is a point. This right here is a point. And this right here is a point. And we see every input, so 4 is an input, 6 is an input, 10 is an input, has exactly one output. So 4 gives you 5, that's my output. 6 gives you 7, that's an output, and 10 gives you 3. So that would be a function. This would not be a function. So let's say I switch this up. Let's say I just had this happen. We see every input has exactly one output. That's the definition of a function. So 4, my input, is 5, but 4 is also 3. So this is not a function. Okay. It's not a function. Now the domain of a function is the set of all possible input values of it. These are the x-coordinates. The range of a function is the set of all possible outputs. These are the y-coordinates. We'll go over those in a second, okay? So for example, let's say g equals, curly bracket 1, 4, 3, 9, 10, 2. Is it a function? And if it is, what is the domain and range? So it is a function because we know g of 1 is 4. So my input spits out my output 4. G of 3 is 9, and G of 10 is 2. There's no ambiguity there. The inputs 1, 3, and 10 have exactly one output. Those are 4, 9, and 2, so it is a function. The domain is the set of all input values. These are the x-coordinates. So the domain is a set. It's got a curly bracket because it's a set. It includes 1, 3, and 10. So that's the domain of that function. The range of this function is a set of all possible y-coordinates. So if we look at the y-coordinates, this is the x, this is the y. It's 4, 9, and 2. So the range of this function would be 4, 9, and 2. Let's consider h. Okay, here's example 2. Is this a function? If it is, what is the domain and range? Does every input have exactly one output? Well, 3 goes to 10, it doesn't go to anything else. 4 goes to 1, it doesn't go to anything else, so it is a function. So yes, it is a function because of this. The inputs 3 and 4 have exactly one output, 10 and 1. And the domain of this function is 1, 3, and 10. And the range is 4, 9, and 2. Well, that's clearly wrong. What is the domain here? Well, the domain is 3 and 4. So let's change this. These are my x-coordinates, 3 and 4. And the range is 10 and 1. So let's change that. So the range should be 10 and 1. I had this in here just to kind of convey that message. So yep, that's how you do that. So let's talk about example 3. Let f be 2, 5, 7, 8, and 2, 10. Is it a function? If it is, what is the domain and range? So let's look here. Well, we know f of 2 equals 5. Okay? F of 2 is 5. So that's the notation right there. It spits out 5. But we also know f of 2 is 10 because here's 2, it's 10. Now these things should be equal to each other. Does 5 equal 10? No, this doesn't even make sense. So this is not a function. Every input, 2, 2, should have exactly one output. These should both be 5 or these should both be 10. So this is not a function. Every input has to have exactly one output to be a function. Here the input 2 has 2 outputs, 5 and 10, so it is not a function. Let's talk about example 4. Does this mapping below represent a function? Well, we see the input is 1, and then the output is 3 and 4. So since you have one input and going to 2 different places, 2 outputs, this is not a function. So it is not a function because f of 1 is 3 and f of 1 is 4. It's going to 2 different places. It has 1 input and 2 outputs, so it's not a function. Now, a common set we use in math is the set of all real numbers. The set of all real numbers is this double-legged R looking thing over here, and it has everything in it. It doesn't include infinity, it doesn't include negative infinity, but it includes all numbers. It includes 0, it includes negative numbers, it includes irrational numbers, it includes fractions, it includes everything besides infinity and negative infinity. So these are all the real numbers. Now the notation of a function is f from a to b. So this is how we would read this off. F from a to b means a is the domain and b is the codomain. We will explain how the codomain relates to the domain with this example below. So here, let f be a function where r is the domain, all real numbers is the domain, and this is the codomain. How do I know this is the domain and codomain? Because the domain comes first, and then the codomain is second. Be given by the rule f of x equals x squared. So let's just consider this. So the domain is all real numbers, so this means we could plug anything we want into this. Well, we know f of negative 2, we replace x with negative 2. Negative 2 squared is negative 2 times negative 2, which is 4. So my input is negative 2 and my output is 4. If we look over here, f of negative 1 squared is 1, so negative 1 becomes 1. My input is negative 1, my output is 1. F of 0, well 0 squared is 0, my input, my x-coordinate is 0, my output y is 0. My input is 1, my output is 1 here, because 1 squared is 1. And then if I plug in 2, well 2 squared is 4, so this plots the point 2, 4. So if we look over here and we wanted to plot this thing, well we know it contains these points on it. So let's just scroll on down. We know it contains the point 0, 0 because that's on here, 0, 0. We know it contains 1, 1 because that's on here. We go over 1, up 1. And we know 2, 4 is on here, so we look at 2, 4. We go over 2, up 4. It's plotted there. And we also know we have this kind of symmetry going on. So at negative 1, it's 1. At negative 1, it's 1. At negative 2 squared is 4. At negative 3 squared is 9. So we plot these dots, and we have this smooth curve that we connect between them, because we know we can put all these points within this function here. So this gives the plot below. So the domain is all real numbers, and we see that the range is all real numbers greater than or equal to 0. Now what the range is all of the values that are the y-coordinates. So let's look at let's look at this value right here. So my y-coordinate is 0, right? It includes 0. It also includes 1. It includes all of the values between 0 and 1. So the range includes all of these y-coordinates along here. The domain is all of what x can be. X can be all real numbers. The range is what y can be. So it's from 0, and it includes 0, and it goes all the way to infinity. So in other words, all real numbers greater than or equal to 0. Notice that the codomain, though, if we look back here, the codomain was all real numbers. That's fine that the codomain is all real numbers. Which includes all of the values of the range. So we know that 0 is in that, and indeed the range is a subset of the codomain. So the range of a function has to be a subset of the codomain. Every value of the range has to be contained within the codomain. I don't know when you would want to say that the codomain of this function is indeed all real numbers, because really the codomain could be all values from including 0 all the way up to infinity. So in other words, if we're going to really redefine what the codomain was, it would make more sense for it to be all real numbers greater than or equal to 0. Ideally, when we talk about range and codomain, we want the range to equal the codomain. So a lot of times in your homework, you'll say, well, what is the codomain of this? And they'll just plot this. Yes, the codomain could be anything as far as like all real numbers. All real numbers would work for all of these. But really, the codomain, we want the codomain equal to the range, so it's all values from 0 to infinity. All right. I also want to talk about set builder notation and interval notation. So set builder notation is like this. And a lot of times we'd actually have it, x is in real numbers. I'm just kind of abbreviating the notation here. So this means that x such that x is a real number such that x is between 2 and 4. So what this does is it includes the values 2 and 4. And we define this as a closed interval. A closed interval includes 2 and 4. So this is my interval notation over here. It's all values, so 2.5 lies within this. So we know 2 is in there. We know 2.1 is in there. We know 2.3 is in there. We know 3 is in there. We know all of these values are in there, and it goes all the way up to 4. So this is the set of all real numbers between 2 and 4, and it's inclusive of those values 2 and 4. So whenever you have this closed bracket here on both sides, this is called a closed interval. We'll get to open intervals in a second. This is a set in set builder notation. This is x such that x is a value not including 1 and including 5. So x is between these two values here. So if we think about all of the values between 1 and 5, well, we know 1 is not in there. We know 1.0001 is in there, but we know 1 is not in the set. So we have an open bracket. We have an open parenthesis right here. This is open. And then it's at 1, and then it goes all the way to 5, and then it's closed over here. So it does not include 1. and it includes 5. Let's look over here. So this is another example. So in set builder notation, this is x. 2 is less than or equal to x, which is less than 4. Well, it includes 2, and then it goes all the way up to 4, and it does not include 4. So that's how that notation would be represented there. And this would be open on both of these. This is an open interval because these are both less than, and it's like that. X such that x is less than 1 includes all real numbers less than 1. That goes from negative infinity. It's open at negative infinity. It's not closed. We don't want to include negative infinity because negative infinity is not a real number. And it goes all the way to 1. So these sets would be equal. And this is the set of all real numbers such that x is greater than or equal to 5. So it's from 5, it includes 5, all the way up to infinity. So this is set builder notation over here, and this is interval notation over here. So a lot of times I'll see students write this stuff. So note that this doesn't make much sense. So negative 5 to negative infinity, we don't want to write it like this. Always you're going to put the value that is less than on this side over here. So the value that is less than should be on the left side. The value that is larger should be on the right side. So and in fact, if we're considering, this situation here, we think of all the values between negative 5 and negative infinity. Well, there's nothing in there. So this means this. So a lot of times, instead of writing it like this, we would want to write it like negative infinity to negative 5. So we would ideally want to write it like this to include actual real numbers in that set. So let's talk about this example here. What is the range and domain of the function below? So let's look at this function here. So the domain is what x can be. So x can be literally anything. So the domain is all real numbers. The range is what y can be. So if we think about what y can be, well, it can be 0 because we know 0 squared is 0. The negative of that is going to be 0. So we think about 0 and we have negative infinity. Now, a lot of times I'll see students write it like this, which is not correct. And instead, because this negative infinity, we want to include values for the range. So we'd want to instead have it switched so it's like negative infinity to 0 is the range. It starts all the way down here, all of the y coordinates down below, and then it goes all the way to 0, and it's closed at 0. It's not open. This would be bad. And this would be the range of that function. The range would be that. Again, the domain is all real numbers. The range is negative infinity to 0. And if someone was to ask, what is the codomain here? Well, we want the codomain to equal the range unless mentioned otherwise. Now in your book, a codomain is said to be all real numbers. It's just kind of odd that they do that. So in general, the range is what the y coordinates are, and the domain is what the x coordinates are, all of these values. And we want the codomain to equal the range unless mentioned otherwise, and I'll specify those situations there. Well, let's talk about this. Well, what is the domain and the range of this thing? Well, the domain, let's think about what the first value it could be. The first value it could be for my x coordinate, because the domain is your x coordinate, is negative 3. So it's negative 3. Now, it's closed at negative 3. It it includes the point -3, so I'm going to close it, use a close bracket. It goes from -3 all the way up to 3, and it's open at 3. So I go -3 to 3, I write it's open at 3. And then what we're going to do is, to denote the domain here, we're going to use this union symbol. What this union symbol means, it takes on all of these values for the x, and it could also take on these values over here. These values over here are 4. I'm sorry, not 4. It includes 3. That's my x coordinate right there. And it goes all the way to 4. So we're going to write 4. And it's open at 4. So that's the domain. A lot of times this is the union symbol. It's denoted with the word or. So it could be all of the values in this set or all of the values in this set here. So we just use that U symbol. The range, let's think about what the range is. Well, the range includes -1. The range is what y can be, so it's from -1. And then it goes all the way up to 3. So all of the y coordinates are from -1 to 3. So the range would be -1 to 3. Notice how they're both closed because it actually hits those values. Even though it's open here, it hits it over here. So we keep it closed because we want to include that point right there. Then I want to talk about what continuous functions are. Well, we can go into like the exact definition of continuity. It's like, it would be such an overkill though. So a function is continuous if it can be drawn with one curve. A continuous function is something I can place my pencil down once and then continue drawing it smoothly throughout the entire thing. If I look over here, this is a continuous function. I can take my pencil and draw this whole object. And if I was to do this function over here, I was to take my pencil and I was going to draw this. And then I'd actually have to jump from here to here. This would not be continuous. This would be a discontinuous function. And actually it's called a jump discontinuity because we have to physically jump to go from here to here. There are also infinite discontinuities that kind of drop off here and then go to -infinity and go up to infinity on this side over here. So this would be not continuous over here. This is continuous. This is also a not continuous function. Notice it jumps from here to here. And this over here is not a continuous function. It's not drawn as a smooth curve. If we look over here, let's consider the domain to be integers. So here, the domain is just 0, 0 squared is 0, 0, 0. It doesn't include all of the other values between. So since the domain is integers, well, we know 1 squared is 1. We know 2 is 4. And if we were going to just simply consider the domain to be all integers, this would not be a continuous function. If the domain was all real numbers, and we consider this function, it would be continuous. This is a not continuous function. We're jumping all over the place. So a discrete function is a function with separate unconnected points. Okay, we can go over this. But for this class, we're just going to talk about discrete functions as a bunch of points. So whenever you think of the word a discrete function, just think of a bunch of points. So let's go over here. A discrete function is a bunch of points. There's no smooth curve over here. So this would be a discrete function. This is discrete. These are examples of discrete functions. These are examples of continuous functions. Over here, they're smooth curves. A function can be neither discrete nor continuous. An example of that would be it's got this discrete kind of action going on over here, and all of a sudden there's a little region that is continuous from here to here. That would be an example where it's neither discrete nor continuous. It's continuous along this interval over here, but it's not throughout the whole domain. So that was the presentation to kind of help you if you get stuck.